Okay, so hello everyone, welcome to my new MS channel. So today we are actually entering in the first topic of Form 4 of MS, that is Chapter 1. As you can see, the chapter name is Functions. So this might be the first of many more YouTube videos that I'll make. So hope this content is going to be useful to everyone who is going to listen. So let's get started with it and look at maths. So first of all, we are going to look at the first subtopic. The chapter name is functions, and the first subtopic itself is called functions. So we're going to understand this word deeply. So first of all, why I put this as the first slide is we are not going directly to the syllabus, but it's something related to what is going to be told in this subtopic from page 2 until page 11 of your textbook you can refer. So first of all, I want to introduce some lower form maths that will be quite useful when we talk about functions. So functions, you see, we have two types. So the first type is one to one, and the next type is many to one. So the common thing here that I notice, right, when they say these two relations, is the ending part, which is one. So the ending part here actually is telling you the word, is telling you a clue that this is actually the image. Whereas the starting part, which is one or many, shows that these are the objects that you might have in a particular function. So these are the two things you'll be dealing here, object and image. So you won't have an image if you don't have an object, but you can have an object without an image. So that's how it goes. Object will map to the image. So conclusion here, a function must only have one image. If it's going to be called as a function, means it can only map to one image. Means there are two possibilities. No? You can have one object to one image, or the second case, it's one or more object to only one image. So yeah, that's the briefing about the meaning of functions. No? So you can see many functions throughout your math syllabus also. Like we have linear, quadratic, cubic, reciprocal, there's many more. That's why we all call that as functions. And also we will learn two more functions after this, which are composite functions and inverse functions. So for them to be called functions, they have to obey this rule over here, these two conditions, one-to-one relation and also the many-to-one relation. So what about non-functions? So although this chapter is talking about functions only, we also have to learn how to identify whether it's going to be a function or not. So if it's not a function, it's going to be pertaining to these two types, which is one to many and many to many. So you see the key thing here, there's a common point which is many at the end, means the image where the object maps to has many images. So let's say we have an object 2, let's say a number 2. So it can map to either 4 or 8. That is a one to many relation where there is one object, but the image can be more than one. So that's why they put there as many. Or you can have many objects mapping to many images. But this one is a bit complex. This one comes from a combination of, let's see, this one is going to come from a combination of more than one object. You're going to go to one image. Or you can have only one object but going to more than one image. So this is the thing here. So we have, when you combine these two, you will get this thing here, many to many relation. Means you combine one to many relation with many to one relation, you will cut off the one and you'll just get many to many in the end. So this is the key point here. Non-functions must have more than one image, but the object is only one and can be many also. But the thing we are concerned about non-functions is focused on the image. Same as functions. It's either one or many at the end. Okay. So when we generally talk about functions, how can they be represented? So actually this one is a extra, something like an extra, but the main three things are here: arrow diagram, graph, and ordered pair. So the most common one tested in NMATS in this subtopic is going to be arrow diagram, because they can relate this to this. They'll give you an equation that represents an object mapping to an image. Graph is usually used in the vertical line test, which I'll tell later. And ordered pair is for you to plot this graph. So all of these are interrelated with one another. So we can go deeper into this to the second page. So the arrow diagram is the most common one you're going to see over here. So let's say now we have four types of arrow diagrams because there are four relations for functions, right? So you see here, I've given four examples of arrow diagrams. So let's go to, so classification of plants. So this one is a bit of bio involved. So those who study Form 5 already will know. So this part, chapter 1. So let's say I give an example. Doesn't mean these arrow diagrams need to involve mathematical numbers. It can be anything. It can be data that is classified. So don't think it has to be involving numbers only. So they can give you a random example like this. So let's see. Let's say we have these plants. So this is facts law, of course. There's no lying about it. So paddy is an annual plant. Silver coxcomb is a biennial plant, and grass is a perennial plant. So you can see where these arrows match to each other. Paddy can only be annual. You cannot say paddy can be biennial or perennial. That's out. So that's why we cannot put the arrow there. And then silver coxcomb is a fact. It can only be biennial plant. It cannot be annual or perennial. Grass also is a fact. It can only be perennial because it goes everywhere. So uh, key thing here, arrow is important to do the mapping, because arrow is going to show you from the object what is the image. These are the two words we will use here: object and image. The left side is the object, the right side is the image, but this one depends on the arrow. So let's say they want to switch. If they put the arrow this way, means object is going to be here, object, and image is going to be here. So whatever it is, the object has to pair to the image. So the direction of arrow will follow that way. So they can interchange as well. Doesn't mean it's only one like that. So this is the note over here. One object has only one image. For this type of relation, one-to-one, as you can see here, the arrow only goes to one part of the circle. So let's say we want to look at another type of relation. This is the function. Let's say I want to go this side also. This side is also a function, many to one. Okay, so this one I go to chemistry, classification of salts. So it can be anything as long as it can be grouped into data. So soluble and insoluble salts. So let's say I give three objects here and three images here. So you can see from here already, zinc chloride, barium sulfate, ammonium carbonate. So you can see that zinc chloride, we know a fact, that's a fact also, just like before. This is soluble salt, so that's why we put an arrow here. And then barium sulfate, we know it's insoluble salts, the fact. And then ammonium carbonate is also soluble. So you can see there's two things clashing here, the one I circle over here. You can see two arrows are meeting at a common point, that is soluble salts. So you can see here that two objects are having one image. So this is the thing. That's why we call it many to one, because there are two objects which is classified as many going to one specific image, soluble salt. So you see overlapping arrows shows more than one object, which is the zinc chloride and ammonium carbonate. They have the same image, which is soluble salts. So this is the key point here, to change color. This. Okay, so one to one, relation and many-to-one relation will combine to form many-to-one relation. Why I say there's a one-to-one relation here? Don't forget, you have a barium sulfate here that maps to insoluble salts. That is only one-to-one. But then this side, this map to this, we have another relation going on here. So two relations simultaneously, you will get an end result of many-to-one. Because finally, the end part, both also is to one. Many, when you compare with many and one, we will get many when you add them up. So makes sense also lah. When you look at it, we will take the majority, the most common relation that you can see here. So yeah, that's how we get this. And these two are functions because they only have one image. So that's the clue over here, huh? One image. So let's see other parts. Okay, one to many relation. Okay. So this one I'm talking about favorite subjects. So this is not a fact, but it can be anything also like this one. So let's say I got four people here, Ali, Abu, Rama, and Mei Ling. So let's say Ali, his favorite subjects are physics and chemistry. And then Rama's favorite is bio, and then Mei Ling's favorite is English. So we are going to plot the arrows from the object to image. Always remember this key point because it will um, translate to many other concepts also in maths where you have the x and you want to find the fx. Later on, you will know what I'm telling. So let's say Ali, yeah, he likes physics and chemistry, right? So you can see this relation over here. One object, which is Ali, is liking two images simultaneously. This occurs simultaneously in real life. So it's one to many images. The many images are physics and chemistry. No? And then you see here, Rama likes bio, one-to-one relation, because one object, one image. And then Mei Ling likes English. Again, you see one-to-one recurring. So you can see here down, scroll down for you. Okay. So you can see over here, one-to-one plus one to many, your end result is one to many. So this Rama to bio and Mei Ling to English is the one-to-one. And one to many is represented by Ali liking physics and chemistry at the same time. So that's how we get the end result, one to many. So the thing to note here is for this function to be called as one to many, I mean, this is not a function. For this situation to be called not a function, it's one object will project to two images, as you can see here. So this is the third time. There are four possibilities. So now we'll go to the last one, which is also not a function. So you can see here. Let's say I want to talk about modes of transport. Okay, that's a good example also. Modes of transport. So I gave here three modes: air, land, and sea, most common. All these three are images lah. Because from this data, which are the objects, we are going to classify them to these three categories of images. So I gave here aeroplane and jet. Both of them are air lah. This is facts. There's three out of these four things are facts. So aeroplane and jet will show the many to one relation because you see there are two objects, but they are both mapping to the same image, which is the air method. And then I gave a random one, ductile boat in Malacca. So I put this as one to many because this can be gone, this transport can be done on the land and also on the sea. So that's why I said one object, which is this, can have many images, land and sea. So from here you can see there are two relations going on again. Only one-to-one relation is just direct. There's no combination. But other than that, when you involve many already, the word many enters, as you can see here, it's going to have combination of relationships to form an end result. which is many to many. So yeah, so this one, the condition is, there are two conditions going on actually here. Okay, so one object can have more than one image, or more than one object can have also one image. So this is the thing that shows all the four things represented by arrow diagrams. So these things you can actually find in the graph where they'll give you numbers. Of course, you can't plot this stuff on the graph because they are categorical data. They're not numerical data. So graph can only represent numerical data if you are drawing the line graph, let's say. So that's the thing over here. So I think it should be okay. So let's continue. Okay, let's go to the next page. Third one. Okay, so this is an important statement on top here. So only from a function, you can get an equation. That's one thing, because when you form a function, it actually comes into an equation. Let's say fx goes to 2x. So this is a function which is a type of linear equation. So that's the relationship. So fx can also mean y. In our normal situation, we always say as y because that's the image we are respecting to in a graph. X is usually the object and y will be the image. So fx is just a substitute for y in this chapter, because we rarely use y in this chapter since we are finding functions, and functions have to be represented by this kind of f colon x thing, something like this. So as I said just now, we have four types: common one, linear, quadratic, cubic, and the reciprocal. So these are the common ones we learned, and all these are functions, and it can be proven with one test that we will do very soon, and you'll see why all of these they are called functions. It's very normal to hear them like they will say this is a quadratic function. Why they actually say quadratic function? The word function at the back, they can just say quadratic, but since it's a function, they'll add the word function there, and there is a justification actually. So all of the above graphs, they are actually functions. So I just gave a kind of conclusion here. So the graph sketching is actually related with the ordered pairs, because if you realize ordered pairs are in the form of coordinates where you have the x coordinate and y coordinate. So from there, you're going to sketch your graph to determine whether it's going to be a function or not. And then you will plot the graph and you observe the shape. So from there, you can interpret, is this shape representing linear, quadratic, cubic, or reciprocal? So that's how it goes. And then the equation or general formula, why do we need that? Equation can also be used to actually determine the shapes based on memorizing x power what, like linear x can only be power 1, if quadratic x power 2. And then so when you have the equation like this, let's say we know our constants, the value such as a, b, and c. So from there we can just substitute random values of object. And when I say object, means I'm telling about x in this chapter, to find the image which is represented by y or fx I can add, since we always see the word fx over here in this chapter. So now we come to it, the vertical line test. So this is a common question they can actually ask you in paper 1, because it's a short thing. They'll ask you, is this graph a function? And then justify your answer. So this is the justification to the vertical line test. So let's get into it. Vertical line test. So this is an indicator to see whether the graph we plot is a function or not. So let's say I draw this graph over here. So at first glance, if you may, I won't say may, you should be able to recognize this is actually a cubic function based on the shape of it. So you can see here when I do a vertical line test, this one over here. Can you see the point? How many points intersects the function? You can only see one when you draw a vertical line. So this indicates it's a function. And then let me explain. Because when you do vertical line, right, you're only going to have one object here on your x-axis, and you have one coordinate here that will project to the y-axis, and you'll have an image. So one object with one image. So that is a one-to-one relation actually for this x power cube graph. So that's why we say it's a function, because one-to-one relation it will come out as a function. But you see in this case, if this kind of graph, it does exist, hard equation. So you can see when I draw a hard equation, if I do a vertical line test here, you're going to see something. You will see there are 2 points. So that is why this is not a function. Because for the same image, for the same object, when you see here, right, I cut the x-axis at this point. Means this point on top here and this point at the bottom here, let me zoom in. They are actually both sharing the same x coordinate, which in turn means they have only one object on the x-axis. But when they project to the y-axis, they have two images here. Means what can I say from here? This is actually a one-to-many relation, because one object on the x-axis has two images on the y-axis. So there's a one-to-many relation going on here. And whenever there's many at the end part of the statement, means it's not going to be a function already. And how I prove it is with this vertical line test. So that is the importance of this test, just to know it a bit deeper, not just memorize. Vertical line is for what? Whether function or inverse function, but it's actually the understanding behind why we do this kind of test, so that we can determine how many objects and images for a certain graph function. Okay, so this is the notes for this part. I think it's quite clear. So let's go on. Okay, so justification behind the vertical line test, as I said just now. Vertical line will only, it's only going to point at one object on the x-axis. You can see just now. For it to be called as a function, then we can determine how many y coordinates can we have from a graph. So one good example here is we see the idea of limit in a function. So this graph is quite famous if you have seen before. We'll have like one shape like this, and then it's like reflected on an axis like this and forms a shape like that. So you can see here this, when I put a vertical line in between these two graphs, you can see that the line will never intersect the graph. So this is also another favorite question in chapter 1 functions. So let's say the equation is this for this curve, x over x minus 1. And this condition is the one that will tell you a lot of things. X cannot be 1 because let's say I want to substitute x cannot be 1, right? At the denominator, you will get 1 over 0. So you're going to get an infinity in the end, which we don't want to happen in any chapter in this NMAT syllabus. This is what we don't want. So that is why we have this condition you have to write here. In any subtopic of this chapter, we have to state this condition if the denominator has a variable like x. Okay, so this is the proof of this idea of limits thing. So you can see the vertical line and the graph will never intersect at x equals 1 and approaches infinity. You can keep on trying to plot, substitute random x variables into this equation, but you'll always find out that you can never get the value that will intersect x equals 1. You can come as close as 0.999999 and it will continue like that, but it won't touch number 1 exactly. So this is the thing. And another example also quite relatable to you if you have studied Form 5, Chapter 6, we go. Another good example to show you over here to the tangent graph. So a bit special from your sine graph and cosine graph because sine graph and cosine graph, they are in a continuous cycle. But you can see here it's not continuous. It's like cut halfway and then it continues. So y equals tangent x. Any tangent graph, but I took the most basic one lah. Since we're not talking trigo here, we are doing functions. So just an example. So this is another idea of infinity. When x is 90 and 270, you can try with your calculator. So you can just put tangent 90, you will get maths error. So why they say maths error? Because it's infinity. The function is undefined. Infinity and undefined is the same thing. So when 270 also is the same, this will repeat every 180 degrees after every cycle. So that's why you can see a consistent pattern here. So that's why you see the graph will come close to 90 degrees, but it won't touch. It'll just go up exponentially. Same with here. It won't touch. Here also it won't touch. And here also it doesn't touch. So yeah, kind of similar kind of graphs lah, like this. This one also will not touch the x-axis. It'll just continue. Same with here. So this is the idea lah of functions. Okay. So next, important terms in this subtopic. So let's see. Okay. So again, we are using the arrow diagram here. Let's say I have a function, same color. This one. So fx is x plus 1. Let's say this is my function. So I have these relations here that obey this function. 1 to 2, 2 to 3, 3 to 4, 4 to 5. I didn't map this last one lah, just to create the question for you all. So let's see here. Domain. Okay, so these are the few questions they can ask. 1 mark, 2 marks like that in your paper 1. They will say, state the domain. So we got to know what is actually domain. So domain is actually anything that is called as the object, which is on the left hand side. Not necessarily, but it's the starting of the arrow here. Domain will always start from the arrow, where the arrow starts. That's the domain. And you have to put this curly bracket. If this one is, if we just put a normal bracket like this, it's not considered as correct lah. Although your numbers are correct, it has to be in the form of the curly bracket, like how you do your sets in your mathematics. So the same concept. And codomain will be whatever on your right hand side, which is the image. So image, we have few common ones we use to represent, which are fx, gx, hx. These are just some common examples I share here. So it can be anything, any alphabet you like, but these few are the ones commonly said in the exam. So okay, so codomain can be 2, 3, 4, 5, all this. But range, this is the special one here. Range of relation. So why I don't put 2, 3, 4, 5 for the relation here, it also has a reason. Wait, not 1, 2, 3. Sorry, 2, 3, 4. This is 2, 3, 4. So why I don't put 2, 3, 4, 5? Because can you see any arrow here mapping or not? This is the key part. From 4 to 5, there is no relation that's happening. So that's why I just write 2, 3, 4, because these 3 numbers are being mapped by 3 arrows from the object. But 4 and 5 are like separate cases. So range is only something that is within the function given. We cannot plot or put any values that do not satisfy the function given. So that's why it's not included in the range. Range also we use this curly bracket, same thing. Okay, so let's see here. The note is what is not mapped in the arrow diagram is not part of the function, cannot be considered as the range. So that's the thing here. That's the difference between codomain and range. Sometimes codomain and range can have the same numbers if all of the arrows are mapped, but it can also not have. Depends on your function in the end. Okay, so let's continue here. Here's another part that is not really famous, but it can come out as a short question also lah. So let's see. Two types of functions, discrete and continuous. Later, if you go on to your chapter 5 or form 5, you will see these two words at the beginning itself, discrete random variable and continuous random variable. But they also appear here in this first chapter, which is functions. So they're trying to bring out a concept here before you enter that chapter, which is how do we see a graph is discrete and how do we see whether a graph is continuous? Actually, quite simple. You just interpret the meaning by itself. Discrete means it's separated. It cannot be connected by a line or a smooth graph. Means it's like separate and individual cases. Whereas continuous, if you see, the points can be connected. Means there is a relation between them and it can be connected with a straight line or curve. So when you enter your chapter 5 or form 5, you will learn two important things in statistics field. So this is what we call as binomial distribution. So it is classified as discrete because you can see the points here. You cannot plot a smooth graph with these points because you will get something like this, which is not that accurate compared to this on the right hand side. So you see, I can see clearly here. You can see on the x-axis, which is x, you have numbers like 1, 2, 3, 4. But then on your y-axis, right, you can see that certain points share a common image, and some have one object to one image. So you can see that it's very discrete. All these numbers on the right hand side actually represent probability. 3 over 16, 5 over 16, 8 over 16. This is the probability of an event when the x value is as such on the x-axis. So we can't form a smooth curve. When you look at the right hand side, you can see that this is actually a bell curve or normal distribution we call when you learn in 1 chapter 5. So you can see that the data is actually distributed evenly, not like just now. In here you will have intermediate values, whereas there you have no intermediate values. It's just this and that. But here we have many values in between. You can see that your z score can fall anywhere in between of this graph. So this is why we call it a continuous graph. It forms a continuous cycle and it goes on up to the end. Whereas there it has a limit, it can stop somewhere. So this is the thing here to show whether continuous or discrete. Okay, so this is the thing here. And then we are coming to an end already for this subtopic. So just a few more common ones. Okay. Okay, let's say I give you a function fx equals 2x plus 1. How to read it? This is something that might not be important for exam, but just for knowledge purposes, because we will say fx arrow 2x plus 1. Let's say I want to read this without knowing how to read first. So the actual way to read this is function f. So why they actually keep on putting this sign f in front, the alphabet is actually trying to represent a function. Function that is labeled as f will map x. X is the object over here. That's why you see x appearing at the image again. X maps the x, which is the object, to 2x plus 1. This whole thing represents the image. And we are going to substitute that particular object to get the value of this image, 2x plus 1. Just like your linear equations. You have to find your y when you know your x value. The same concept here. So some exercise here. So let's say based on this function, 2x plus 1, I have they asked to find the image of 4. So this can be slightly confusing because is 4 going to represent your image object? So this one actually a bit of English. You have to read the statement carefully. So you can see here, find a nice color. Okay, so find the image. You stop here. Don't read further on. They ask you find the image. Means whatever at the back here is definitely going to be your object because they asked to find the image already. If image is going to be represented by fx, of course, in this case, because the function I gave on top here is fx equals 2x plus 1. So that is your image. So what we are going to do is image of 4. So we know your object is 4 means your x is 4. X is your object. So fx is 2x plus 1. So you're going to substitute. You can put a statement here to guide the examiner what you're actually doing here. You can write substitute x is 4 and then you proceed here. So you'll ganti this with this. X is 4 and also show this part. This part is going to earn you 1 mark here. Whenever you show substitution in admaths, you always earn marks and your final answer is 1 more mark. So maybe this is 2 marks lah. Or they can also be 1 mark for your final answer itself because this is a simple, very basic operation for this chapter. So yeah. So next question, they said find the object of I. So again, whenever you say find the object, you already put a barrier there, don't continue. After the off is going to be what you're going to substitute in your equation later. They say find the object means 5 is going to be your image indirectly. So image we represent with fx. So your fx is going to be 5 here. So what we do is we're going to find your x. So how to find x? Fx is 2x plus 1. Always copy back the equation. It's a good habit to practice because you'll know what you're doing in the end. But don't copy it wrongly, that's the only thing. So you put fx as 5 and then you solve, you will get x is 2, your basic algebra. So this is the object that can give you an image of 5 in this equation of fx is 2x plus 1. You can try back. Let's say I put x is 2 back into this equation. Don't you get 5? 2 times 2 plus 1 is 2, 5. So your answer makes sense. That's how you check it. So yeah. Another one, this is a very, wait. This one is a very hot question that they like to ask. Find the value of x that maps to itself. This statement won't give you any clue what they're actually asking you to find actually, but actually very easy. What they're telling is what x value, which is the object, can get you the same value of fx, which is the image. So that's the thing here. So that's why I make this assumption. Let fx equals to x means both these values are going to be same. So it's equal. So fx you have on top there, the question 2x plus 1 equals to x. This is what I added here. So when you solve, you'll get x is negative 1. Means when you have an object of negative 1 under this function, you will expect to map to an image which is fx also equal to negative 1. So this is a famous example of this chapter they like to ask. So an object that has the same value of image. This is the key point. And another one, important thing to note based on trials and SPM past year. So these are all famous. So let's say I have a function, random one, 2 over x squared minus 9. So they ask you to find the value of x if the function is undefined. So this is another famous one. This time they won't give you the condition here because this is the question. They ask you to find this part here that they didn't write in the question. So undefined means your denominator you must assume as 0 because that is the condition we are going to avoid in all situations. We want to avoid this. So now they're asking you to find the avoided one. So x squared minus 9 is 0, we'll assume. So x squared is 9. Now this is the most important part. Sometimes you will directly solve and you will say x is 3. Which is correct, it's not wrong. But Did you consider all the possibilities of x value? That's the question. When you square root 9, you can have a possibility of 3 and also negative 3. This is the thing here. Because negative 3, when you square back, you're also going to get 9, which will in turn lead you to 2 over 0, which is undefined. So that's why we have to state that x can also be negative 3. Sometimes the question should say values lah to give you a hint, but there can also be situations where they just say value, but you have two answers like this. So don't depend on the question too much. Use your maths knowledge, and you always look for the most possibilities in maths. Especially in your trigo chapter later on, you can have 5 to 6 answers for one question. So maths is about possibilities lah. So always put all the values possible for your answers, especially when you go to the next chapter, chapter 2 quadratic, you will have two x values. You'll reject one, you'll accept one. So all this is based on situation and reality concept, no? Daily life situations that force you to reject one value. But in this case, this chapter, there's no situation created. It's just a normal question, but they want you to tell when it's undefined. So you can have two answers here. Okay. So I think that's quite clear. So let's go on. Last one. This is also a famous one. Very, very famous. Okay. How to go up here? Okay, this is a modulus function. This one we haven't studied in maths, I think, any time. This is a new thing that has just come to add maths. So modulus function. So what you're going to do here is you have to first understand the concept of modulus. So modulus is only considering the positive. So whenever you talk about modulus, you think positive always. A lot of times in maths, we actually reject negative values. Most situation, I would say maybe 90%. 90% we will always take the positive values in maths for most situations because negative rarely exists. In certain cases, if it satisfies, then okay lah. But most cases, not really. Okay, so let's say I give you an example here. Modulus negative 3, you're going to get 3 as your answer. The negative will be neutralized by the modulus. If modulus 5, let's say this is already positive, so what answer can you get? Also positive, lah. Because modulus, the end result should be positive no matter what. So then another example, x square plus 9 is 0. So when you modulus this, you have to add a positive and negative to your integer at the right. But since this case is 0, positive 0 or negative 0, no effect. What 0 is 0, it's not positive. It's neither positive nor negative. So it doesn't affect your final outcome. So let's say I give you an example here. This time with the value at the right hand side, of course. So x cube modulus x cube plus 6 equals 2. So you have two chances again here, as you saw before. So you can either say x cube plus 6 equals 2 or x cube plus 6 equals to negative 2. So the negative comes after you modulus the equation. So don't automatically write positive, negative here. You have to take out the modulus sign first, then only write your positive, negative. That's how it works. So you will expect two x values lah, x1 and x2 is what. So that's the thing here for modulus. And this is a very good example to show you about this modulus equation with a graph. So I have two graphs here. So with the same function, you can see how it affects this modulus thing. Okay, let's say this. Let me change color. Okay. So fx equals modulus 2x minus 4. But here, I just give fx is 2x minus 4. The difference here is modulus lah. It's the difference that I'm applying here. So you can see here. So what I do is what I said before, we just plot random values into your equation. But always make sure this random values 1, we have to make an assumption that one situation x is 0 and one situation your fx or the image is 0 in order to intersect the graph at the y-axis and x-axis. because only if you intersect, you'll be able to get a correct shape. Let's say I don't put this point here. You see the graph, it comes like this. So weird, which is not representing like a linear equation function also. It will come like a quadratic curve, which is wrong already. So that's why we have to plot most points as possible to avoid the shape from going somewhere that is not correct. So you can see here, you will only get a graph on the positive side of your x-axis. Why the graph doesn't go down here is because we already modulus the value. You can see if I put x is 0, you will actually get fx is -4, modulus -4. But when you modulus -4, you're going to remove the negative sign because it's neutralized already from the modulus. So you only take the positive value. You see, so I put 4 here, not -4. Another example 1 also, you should get -2, but I put 2 because of the modulus sign here. If 2 0 is okay lah, you modulus 0, you still get 0 no matter what. 3 and 4 onwards, you already get your positive answers. So that one doesn't care whether it's modulus or not. So this is the graph shape over here. You can see it's like a V shape like that. This is straight line. Don't draw curve here. The graph's supposed to be linear equation. So that's why we put a straight line. So yeah. So you can see in the next example here, without the modulus, what is the effect happening on this graph? Okay. So you see, I'll plot the negative values here, -4 and -2. But here it's all positive based on the equation. Here we follow, we don't care whether it's negative and positive. So you can see the result here. Originally the graph was like this, right? But you see what happened to this part? It actually reflected down to the y-axis, as you can see over here. This is the effect of the modulus. It turns everything that is negative down here into something that is positive up there. With the same range, from 0 to -4, I will reflect it upwards, 0 to 4. Same value. So it's actually kind of like hiding the truth of what's the actual function looking like. So this is why we have modulus. So that is commonly used to show positive relationship. So I think that's all for the sharing of chapter 1.1 functions. So I hope that it actually helped a lot and you can understand functions better. So continue staying in tune for more videos.